Question 1. An electric dipole with dipole moment 5 times 10 to the power minus 6 coulomb times m is aligned with a uniform electric field of magnitude 4 times 10 to the power 5 Newton divided by c. The dipole is then rotated through an angle of 60 degrees with respect to the electric field. The change in the potential energy of the dipole is. Correct answer is option D. Potential energy of an electric dipole in a uniform electric field is given by U equals P cos. Now let us consider electric dipole. An electric dipole is a system of two equal and opposite charges separated by a small distance, characterized by a dipole moment vector directed from negative to positive charge. Change in potential energy is given by U equals F U I equals P cos F plus P cos E. Let us examine potential energy of dipole. The potential energy of a dipole in an external electric field depends on its orientation and is minimum when aligned with the field and maximum when opposite to it. Thus, U equals P cos E cos F. Substitute values. P equals 5 times 10 to the power minus 6 coulomb times m, E equals 4 times 10 to the power 5 Newton divided by c, I equals 0 degree, F equals 60 degree. U equals 5 times 10 to the power minus 6, 4 times 10 to the power 5, cos 0 degree cos 60 degree. U equals 5 times 10 to the power minus 6 times 4 times 10 to the power 5, 1 divided by 2. U equals 2 times 1 divided by 2 equals 1 joule. Thus, the change in potential energy is 1.0 joule. Question 2. Two identical charged conducting spheres A and B have their centers separated by a certain distance. Charge on each sphere is Q and the force of repulsion between them is F. A third identical uncharged conducting sphere is brought in contact with sphere A first and then with B and finally removed from both. The new force of repulsion between spheres A and B is. Correct answer is option B. When two identical conducting spheres are brought into contact, charge is equally distributed between them. Now let us consider charge distribution. In conductors, charge redistributes uniformly over identical bodies when they are brought into contact, resulting in equal sharing of total charge. Initially, charge on A equals Q and on third sphere equals 0. After contact, each gets Q divided by 2. Let us examine Coulomb's law. Coulomb's law states that the electrostatic force between 2 point charges is directly proportional to the product of charges and inversely proportional to the square of the distance between them. Now third sphere, Q divided by 2, is brought in contact with sphere B, Q, so total charge becomes Q plus Q divided by 2 equals 3Q divided by 2. After redistribution, charge on B equals 3Q divided by 4 and on third sphere equals 3Q divided by 4. Final charges, A equals Q divided by 2 and B equals 3Q divided by 4. Initial force F equals kq squared divided by r squared. New force F equals k, q divided by 2, 3q divided by 4, divided by r squared equals 3 divided by 8, kq squared divided by r squared. Thus, F equals 3 farad divided by 8. Question 3. A metal cube of side 5 cm is charged with 6 C. The surface charge density on the cube is. Correct answer is option D. Surface charge density is defined as charge per unit surface area, sigma equals Q divided by A. Now let us consider surface charge density. Surface charge density is the amount of electric charge distributed per unit area on the surface of a conductor. Total surface area of a cube is 6 A squared. Let us examine surface area of cube. The surface area of a cube is given by 6 times the square of its edge length, as it has 6 identical square faces. Given, side A equals 5 cm equals 0.05 meter, charge Q equals 6 C equals 6 times 10 to the power minus 6 coulomb. Surface area equals 6 A squared equals 6 times 0.05 squared equals 6 times 0.0025 equals 0.015 meter squared. Surface charge density sigma equals Q divided by A equals 6 times 10 to the power minus 6 divided by 0.015. Sigma equals 4 times 10 to the power minus 4 coulomb m squared equals 0.4 times 10 to the power minus 3 coulomb m squared. Thus, the correct answer is 0.4 times 10 to the power minus 3 coulomb m squared. Question 4. The value of electric potential at a distance of 9 cm from a point charge 4 times 10 to the power minus 7 coulomb is, given 1 divided by 4, equals 9 times 10 to the power 9 Newton m squared c squared. Correct answer is option D. Electric potential due to a point charge is given by V equals kQ divided by R. Now let us consider electric potential. Electric potential at a point is defined as the work done in bringing a unit positive test charge from infinity to that point without acceleration. Here K equals 1 divided by 4 is Coulomb's constant. Let us examine Coulomb's constant. Coulomb's constant is the proportionality constant in electrostatics that determines the strength of interaction between charges in vacuum. Given, Q equals 4 times 10 to the power minus 7 coulomb, R equals 9 cm equals 0.09 meter, K equals 9 times 10 to the power 9. Substitute values. V equals 9 times 10 to the power 9 times 4 times 10 to the power minus 7, divided by 0.09. V equals 36 times 10 to the power 2, divided by 0.09. V equals 3600 divided by 0.09 equals 4 times 10 to the power 4 volt. Thus, the electric potential is 4 times 10 to the power 4 volt. Question 5. A thin spherical shell is charged by some source. The potential difference between the 2 points C and P, in V, shown in the figure is, take 1 divided by 4, equals 9 times 10 to the power 9 psi units. Correct answer is option D. In a charged conducting spherical shell, the electric potential is constant throughout the interior and equal to the surface potential. Now let us consider conducting spherical shell. In electrostatic equilibrium, all excess charge resides on the surface of a conductor and the electric field inside is zero, making the potential constant everywhere inside. Hence, potential at any internal point, C, is equal to the potential at the surface point, P. Let us examine electric potential inside conductor. The electric potential inside a conductor in electrostatic equilibrium remains the same at all points because no work is required to move a charge within it. Thus, Vc equals Vp. Therefore, potential difference V equals Vc, Vp equals 0. Thus, the required potential difference is 0. Question 6. Given below are two statements, assertion A and reason R. Assertion A, the potential at an axial point at 2 meter from the center of a dipole of moment 4 times 10 to the power minus 6 coulomb.m is pm 9 times 10 to the power 3 volt. Reason R, V equals pm 2p divided by 4 pi var epsilon 0 r to the power 2. Choose the correct option. Correct answer is option. The electric potential due to a dipole at any point depends on the dipole moment and the position of the point relative to the dipole axis. Now let us consider electric potential of dipole. The electric potential due to a dipole at a point is defined as V equals 1 divided by 4 pi var epsilon 0 p cosine theta divided by r to the power 2, where p is dipole moment, r is distance, and theta is angle with axis. At an axial point, theta equals 0 degree or 180 degree, hence cos equals plus or minus 1 and potential becomes V equals pm1 divided by 4 pi var epsilon 0 p divided by r to the power 2. Let us examine axial point. An axial point is defined as a point lying along the axis of the dipole, where the angle between dipole moment and position vector is either 0 degree or 180 degree. Substituting values, V equals 9 times 10 to the power 9 times 4 times 10 to the power minus 6 divided by 2 to the power 2 equals 9 times 10 to the power 3 volt, with sign depending on position. Thus assertion A is correct since potential is pm 9 times 10 to the power 3 volt. However, the given reason uses V equals pm 2p divided by 4 pi var epsilon 0 r to the power 2, which is incorrect because correct axial expression does not contain factor 2. Thus reason R is false and does not explain assertion A. Question 7. According to Gauss' law of electrostatics, electric flux through a closed surface depends on. Correct answer is option B. According to Gauss' law, the total electric flux through a closed surface is determined by the net charge enclosed within the surface. Now let us consider Gauss' law. Gauss' law states that the total electric flux through any closed surface is equal to the algebraic sum of charges enclosed divided by the permittivity of free space, given by Varphi equals frac enclosed var epsilon 0. Thus, the electric flux through a closed surface does not depend on geometrical factors such as area, shape, or volume. Let us examine electric flux. Electric flux is defined as the surface integral of the electric field over a closed surface, representing the total number of electric field lines passing through the surface. If the enclosed charge remains unchanged, the total flux remains constant even when the surface is deformed. Therefore, the correct relation shows that electric flux depends only on the quantity of charges enclosed by the surface. Question 8. A charge QC is placed at the center of a cube. The flux coming out from any one of its faces will be, in SI unit. Correct answer is option D. According to Gauss' law, the total electric flux through a closed surface enclosing a point charge is equal to the charge divided by permittivity of free space. Now let us consider Gauss' law. Gauss' law states that the total electric flux through a closed surface is equal to Q enclosed divided by var epsilon 0, independent of the shape of the surface. The cube is a symmetric closed surface with 6 identical faces, so the total flux is equally distributed among all faces. Let us examine electric flux. Electric flux is defined as the surface integral of electric field over a surface, representing the number of electric field lines passing through it. Hence, flux through one face is given by total flux divided by 6, i.e., var phi face equals Q divided by 6 var epsilon 0. Since the charge is given in microcoulomb, C, it must be converted to coulomb using 1 C equals 10 to the power minus 6 coulomb. Therefore, var phi face equals frac Q times 10 to the power minus 66 var epsilon 0 equals Q divided by 6 var epsilon 0 times 10 to the power minus 6. Thus, the correct answer is Q divided by 6 var epsilon 0 times 10 to the power minus 6. Question 9. If a conducting sphere of radius r is charged, then the electric field at a distance r from the center of the sphere would be V equals potential on the surface of the sphere. Correct answer is option. For a charged conducting sphere, the potential at the surface is related to charge by V equals kq divided by r. Now let us consider electric potential. Electric potential at a point is defined as the work done per unit charge in bringing a test charge from infinity to that point, and for a conducting sphere V equals kq divided by r at the surface. The electric field at a distance r, outside the sphere, behaves as that of a point charge located at the center. Let us examine electric field. Electric field is defined as the force experienced per unit positive test charge, and for a point charge E equals kq divided by r to the power 2. Substituting Q from V equals kq divided by r, we get Q equals VR divided by K. Hence, E equals kq divided by r to the power 2 equals K, VR divided by K, divided by r to the power 2 equals VR divided by r to the power 2. Thus, the correct expression is E equals RV divided by r to the power 2. Question 10. An electric dipole is placed at an angle of 30 degrees in an electric field of intensity 2 times 10 to the power 5 Newton c to the power of 1. It experiences a torque equal to 4 Newton m. Calculate the magnitude of charge on the dipole, if the dipole length is 2 cm. Correct answer is option. The torque acting on an electric dipole in a uniform electric field is given by τ equals pace in. Now let us consider torque on dipole. Torque on an electric dipole is defined as the turning effect experienced by a dipole in an external electric field and is given by τ equals pace in, where p is dipole moment. The electric dipole moment is defined as P equals QD, where Q is the charge and D is the separation between charges. Let us examine electric dipole moment. Electric dipole moment is defined as the product of magnitude of either charge and the distance between them, directed from negative to positive charge. From τ equals pace in, we get P equals τ divided by E sin. Substituting values, P equals 4 divided by 2 times 10 to the power 5 times 1 divided by 2, equals 4 times 10 to the power minus 5 km. Using P equals QD, we get Q equals P divided by D equals 4 times 10 to the power minus 5. Divided by 0.02 equals 2 times 10 to the power minus 3 km. Thus, Q equals 2 mc. Question 11. If contour integral E times ds equals 0 over a surface, then. Correct answer is option D. According to Gauss' law, the net electric flux through a closed surface is equal to the enclosed charge divided by permittivity of free space. Now let us consider Gauss' law. Gauss' law states that contour integral E times ds equals Q enclosed divided by, which relates electric flux through a closed surface to the net charge enclosed. If contour integral E times ds equals 0, then the net enclosed charge is 0, so total inward flux equals total outward flux. Let us examine electric flux. Electric flux is defined as the surface integral of the electric field over a surface and represents the net number of electric field lines passing through the surface. Hence, the number of electric field lines entering the surface is equal to the number leaving the surface. Therefore, the correct answer is that the number of flux lines entering the surface must be equal to the number of flux lines leaving it. Question 12. An electric dipole is placed as shown in the figure. The electric potential, in 10 to the power 2 volt, at point P due to the dipole is, equals permittivity of free space and 1 divided by 4 equals K. Correct answer is option D. The electric potential due to a point charge is given by V equals KQ divided by R, and the total potential is the algebraic sum of potentials due to individual charges. Now let us consider electric potential. Electric potential at a point is defined as the work done per unit charge in bringing a test charge from infinity to that point, and for a point charge V equals KQ divided by R. A dipole consists of two equal and opposite charges, so potentials due to plus Q and Q are added algebraically at point P. Let us examine superposition principle. Superposition principle states that the net potential at a point due to multiple charges is the algebraic sum of potentials due to each charge considered separately. From the figure, distances of plus Q and Q from point P are 2 cm and 8 cm respectively, i.e., 2 times 10 to the power minus 2 meter and 8 times 10 to the power minus 2 meter. Hence, V equals kq divided by 2 times 10 to the power minus 2, kq divided by 8 times 10 to the power minus 2, equals kq, 1 divided by 2 1 divided by 8, times 10 to the power 2. Simplifying, V equals kq times 3 divided by 8, times 10 to the power 2. Thus, the correct answer is 3 divided by 8, qk. Question 13. 6 charges plus Q, Q, plus Q, Q, plus Q and Q are fixed at the corners of a hexagon of side D as shown in the figure. The work done in bringing a charge Q to the center of the hexagon from infinity is. Correct answer is option B. The electric potential at the center is the algebraic sum of potentials due to all 6 charges placed symmetrically on the hexagon. Now let us consider electric potential. Electric potential at a point is defined as the work done per unit charge in bringing a test charge from infinity to that point, and potentials add algebraically. Since the charges are placed symmetrically with alternating plus Q and Q at equal distance from the center, their potentials cancel pairwise. Let us examine superposition principle. Superposition principle states that the net potential at a point is the algebraic sum of potentials due to individual charges. Thus, the net electric potential at the center of the hexagon is 0. Work done in bringing charge Q from infinity is W equals Q, V infinity, equals Q times 0 equals 0. Therefore, the correct answer is 0. Question 14. 2 hollow conducting spheres of radii r and r have equal charges. The potential would be. Correct answer is option B. The potential of a charged conducting sphere is given by V equals kq divided by r, where q is the charge and r is the radius. Now let us consider electric potential. Electric potential is defined as the work done per unit charge in bringing a test charge from infinity to a point, and for a conducting sphere V equals kq divided by r. For both spheres, charge q is the same, so potential is inversely proportional to radius. Let us examine conducting sphere. A conducting sphere distributes charge uniformly on its surface, and its potential depends only on total charge and radius, independent of material. Since r, the smaller sphere has smaller radius and hence larger potential. Therefore, the potential is more on the smaller sphere. Question 15. 2-point charges Q and plus Q are placed at a distance L, as shown in the figure. The magnitude of electric field intensity at a distance r, RL, varies as. Correct answer is option B. For large distance, RL, the system of charges behaves as an electric dipole. Now let us consider electric dipole. An electric dipole is a pair of equal and opposite charges separated by a small distance, characterized by dipole moment P equals QL. The electric field due to a dipole at a distant point varies inversely as the cube of the distance. Let us examine electric field of dipole. The electric field due to a dipole at a point far from it is given by E proportional to P divided by R to the power 3, where R is the distance from the dipole. Thus, E proportional to 1 divided by R to the power 3 for RL. Therefore, the correct answer is 1 divided by R to the power 3. Question 16. Polar molecules are the molecules. Correct answer is option A. Polar molecules possess a permanent separation of positive and negative charges, resulting in a non-zero dipole moment. Now let us consider polar molecule. A polar molecule is defined as a molecule in which the centers of positive and negative charges do not coincide, giving rise to a permanent electric dipole moment. This permanent dipole moment exists even in the absence of an external electric field. Let us examine electric dipole moment. Electric dipole moment is defined as the product of magnitude of charge and separation between centers of positive and negative charges, P equals QD. Hence, polar molecules inherently have a permanent dipole moment, unlike nonpolar molecules which acquire it only in external fields. Therefore, the correct answer is having a permanent electric dipole moment. Question 17. A dipole is placed in an electric field as shown. In which direction will it move? Correct answer is option. In a non-uniform electric field, a dipole experiences a net force due to unequal forces on plus Q and Q. Now let us consider electric dipole. An electric dipole is a system of two equal and opposite charges separated by a small distance, and it experiences both torque and force in a non-uniform electric field. The force on plus Q is in the direction of the electric field and the force on Q is opposite to it. Since the field is stronger on one side, a net force appears. Let us examine potential energy of dipole. The potential energy of a dipole in an electric field is given by U equals P times E, and a system naturally moves in a direction where its potential energy decreases. From the figure, the electric field is stronger on the right side, so the net force on the dipole is towards the right. Thus, the dipole moves towards the right to reduce its potential energy. Therefore, the correct answer is towards the right as its potential energy will decrease. Question 18. Two charged spherical conductors of radius r and r are connected by a wire. Then the ratio of surface charge densities of the spheres, divided by, is. Correct answer is option. When two conducting spheres are connected by a wire, they come to the same electric potential. Now let us consider equipotential. Equipotential condition states that all connected conductors have equal electric potential in electrostatic equilibrium. For a conducting sphere, potential is given by V equals kq divided by r, hence q proportional to r for equal potential. Let us examine surface charge density. Surface charge density is defined as charge per unit surface area, sigma equals q divided by f. Thus, sigma equals q divided by 4r squared, proportional to r divided by r squared equals 1 divided by r. Therefore, divided by equals r divided by r. Hence, the correct answer is r2 divided by r1. Question 19. 27 drops of same size are charged at 220 volt each. They combine to form a bigger drop. Calculate the potential of the bigger drop. Correct answer is option A. For each small drop, electric potential is given by V equals kq divided by r. Now let us consider electric potential. Electric potential is defined as the work done per unit charge in bringing a test charge from infinity to a point, and for a spherical drop V equals kq divided by r. When drops combine, total charge is conserved and volume adds, so radius of big drop increases. Let us examine conservation of charge. Conservation of charge states that total electric charge remains constant in an isolated system, so combined drop has total charge equal to sum of individual charges. If 27 drops combine, then r cubed equals 27 r cubed implies r equals 3r. Total charge Q equals 27Q. Potential of big drop V equals kq divided by r equals k, 27Q, divided by 3r, equals 9, kq divided by r. Since initial potential is 220 volt, final potential equals 9 times 220 equals 1980 volt. Thus, the correct answer is 1980 volt. Question 20. A short electric dipole has a dipole moment of 16 times 10 to the power minus 9 coulomb. The electric potential due to the dipole at a point at a distance of 0.6 meter from the center of the dipole, situated on a line making an angle of 60 degrees with the dipole axis is. Correct answer is option A. The electric potential due to a short dipole at a point is given by V equals 1 divided by 4 pi var epsilon 0 p cosine theta divided by r to the power 2. Now let us consider electric potential of dipole. Electric potential due to a dipole at a point is defined as V equals 1 divided by 4 pi var epsilon 0 p cosine theta divided by r to the power 2, where p is dipole moment, r is distance, and theta is angle with dipole axis. Substituting the given values p equals 16 times 10 to the power minus 9 coulomb, r equals 0.6 meter, theta equals 60 degree, and 1 divided by 4 equals 9 times 10 to the power 9. Let us examine dipole moment. Electric dipole moment is defined as the product of charge and separation between charges, P equals QD. Thus, V equals 9 times 10 to the power 9 times 16 times 10 to the power minus 9 times cosine 60 degree divided by 0.6 squared. Since cos 60 degree equals 1 divided by 2 and 0.6 squared equals 0.36, V equals 9 times 16 times frac 1 divided by 20.36 equals 72 divided by 0.36. Hence, V equals 200 volt. Therefore, the correct answer is 200 volt.